So far, I've talked about electric field around a charged object. Actually, I've only been talking about a small little glass ball with some charge on it. For this kind of a small object, it produces an electric field, a pattern of the electric field, which looks like this. So we get few lines that draw the few lines. They're just straight lines that go out, that radiate outwards from the charge, and I can add arrows to it like this, and then we can say that this is what the electric field looks like. Now when we say this is what the electric field looks like, it means that if I put a positive charge here, for example, if I put a positive charge there, it will experience a force in roughly in the direction indicated by the few lines nearby. If I put a positive charge there, for example, you will have a field in that direction. If I put a positive charge here, the field will be in this direction. And if it is further away, the field will be weaker. And if it is closer to this charge, the field will be stronger. And if it is someplace else on another side, it will be in a different direction. So one of the important feature, although I've not mentioned it so far, one of the important thing about this particular electric field is that it is different. Is that the field strength or the force on a charge is different. Right? The force on another charge is different in different places. If the charge is further away, it will be smaller. The force will be smaller. If the charge is on another side, the force would be in a different direction. If the charge is closer to this ball, it will have a bigger force. So in this sense, we can say that this electric field is not uniform. So it's just one description, this field. So this is an electric field, right? This is an electric field. And this electric field is not uniform. And we're using the word uniform here. We're using the as in same. Uniform as in same. So it's not the same everywhere. Okay, it's not the same everywhere. If you are at a different place, that electric field strength can have a different direction and strength. Now what I want to talk about here, is the idea of a uniform field. A uniform field. So in contrast with this description, right, where I said not uniform means that the force on another charge would be different at different places. So in contrast, if I have a uniform field, that means that let's say down here there is a uniform field. That means that wherever I am around here, the force is the same. Now, so let me start by just drawing the field lines, right, just showing you what the field lines would look like. Now, in a uniform field, the field lines would look like this. They would be parallel. I'm going to explain why in a moment, why they should be parallel, why this means that it has a uniform field. But let me just draw this first, and I'll just say that if I have a field, that is represented by these field lines, then when I have a charge anywhere in this field, it will experience exactly the same force, or force with the same strength and in the same direction. So let's say I'm here. Let's say I have a positive charge here. It will experience a force in that direction with a certain strength. Okay. Now let's say I put the charge there. It will experience a force in the same direction with the same strength. If I put the charge here, same direction, same strength. Uniform field. Alright, so that's what it means. Wherever I am in this region of space, right, the same charge would experience a force with the same strength and same direction. So, but we have two questions here. Alright, we have two questions we need to try to understand here. First of all, why does a series of parallel lines and arrows represent a uniform field, and how can we make a uniform field? I mean, we know how to make a field like that with lines going out from the center. All you need is to take a small object and put some charge on it, and then you get this field pattern, right, with lines coming out from the center. How do you make a field that has lots of parallel lines? Yeah, I'll come on to that. But first, let me try and understand why, if I draw a field with parallel lines and at the same spacing, why would this represent a uniform field? Now, if you recall from this first picture, I have previously explained that the directions of the lines represent the direction of a force if you have a charged object near that line. Okay, and the spacing between adjacent lines tell us something about the strength of that force. So that if we are at another place where the lines are closer together, then the charge will have a stronger force. If we are at a point where spacing between adjacent lines are further apart, then a charge here would experience a weaker force. Now, taking this idea over to this few lines that I drew, these parallel lines that I drew, if I have a charge there, alright, based on these few lines, I would say that the force here would be in this direction, right? Same as the neighboring, the direction of the neighboring few lines. If I have a charge here, the force will be in this direction as well, because it's again the same as the direction of the nearby, the neighboring field line. And since all the field lines are parallel, so wherever I place a charge in this region of space, it will experience force in the same direction. So that explains the direction. What about the strength? Since the strength is supposed to be related to the spacing between field lines, if I put a charge here, you will experience a certain force. Now, if I put a charge there, it would experience the same force just because the spacing between two lines here is the same as the spacing between the two lines there. Likewise for the charge here, spacing between the adjacent lines is again the same. Okay, so this doesn't explain why I get lines like this, but what it explains is why if I can draw the field lines like that, why it is a uniform field. All right, that's just, if you like, the rules of drawing these fields. All right, that's what the rule is. As I've said, you're supposed to draw the electric fields so that where it is stronger, the spacing should be closer together. If the field is weaker, the spacing should be further apart. Okay, so that's how we would interpret this field if you're given a drawing like that. Now let's come to the next question. How, in the first place, do we make a field like this? So let's have a look. Now, imagine taking a piece of metal, say a square piece of metal, maybe a thin sheet of iron, and now let me get two of these. Let's suppose I have two of these, and I'm going to put them close by so that they are parallel to each other. So two parallel sheets of metal, and there is an empty space between them. There's an empty space between them. So I'm just going to support the two. Maybe put some plastic in between to space them out, okay, and to support them, so they won't just be hanging in the air. Then I'm going to connect these two plates to a battery. So say I have a battery here, maybe 1.5 volts. A 1.5 volts battery, and I'm going to connect each plate to one pole of the battery. So that plate connects to the positive pole, and that plate connects to the negative poles. So what happens then? The battery would start producing a current. Okay, I know these two plates are not connected together, so a current would not actually flow continuously in this circuit. But when it is first connected, just for a very short time, some charge will flow, and so some electrons will flow from the negative pole of the battery into here, so that I start getting some negative charges here, and some electrons will flow from that other plate to the positive pole and leave behind some positive charges. But this flow of current will only happen for a short time, and then once I get some charge on it, right, after some charge is accumulated here, the current will stop. Okay, because the reason why this happens in the first place is because the battery has the ability to move, to make a current, to move electrons along this wire. So it generates a kind of a force, which I suppose that's why we call it an electromotive force, an EMF. So it generates some kind of a force that pulls electron out from one plate, that pushes electrons along the wire. Okay, which is why you can pull electron out from one plate and push it into the other plate. But it can't keep doing that, because as this plate gets more positive, eventually it will exert enough attracting force to enough attracting force to prevent further electrons from being pulled out by the battery, and that's when the current stops. But by then this one plate would have already lost some electron to the other plates, and the result is that we have two plates with opposite charges, and it is in between these two plates that we can get a uniform field that looks like this. Okay. So what this means is that if I imagine looking at these two plates from the edge, from one side, let's say that's my eye, okay, and look at it from here, what I'll see are two parallel plates, something like that. I'll see two parallel plates, one on top and one below, and the top one will be this one, for example, the one with the positive charges, and the lower one would be that one, the one with negative charges. So that one. Okay, I'm just to be very clear, I'm just going to call this A, I'm going to call this B. So I'm saying that this is my A and this is my B. So if I look at these two plates from one side, this is what I'll see, the two parallel plates, and inside will be this uniform field. Now of course I won't actually be able to see field lines and arrows. Okay, the field lines and the arrows are just if you like, just a diagram, just things that we draw to help us know that there would be forces in those directions if I put a charge inside. It doesn't mean that there are actual lines. Right? These are just imaginary ideas that we think about. So, but anyway, with these two parallel plates and with the charges, if I have these positive charges spread evenly over one plate and negative charges spread evenly over the other plate, this would be able to create the uniform field that I described.